All right, so weight. After this, you'll understand weight changes in situations where objects are accelerating vertically and able to solve problems in such situations. So I got another video for you here. But before we do that, what is the difference between weight and mass? Weight is how much is being pushed down, and mass is what? How much you are. Okay, so if I get on my scale here, I pull this out for the good example, like, you just happen to have a bathroom scale on your table? I said, yeah, don't you? So the 850 is what? It's in newtons, but it's my weight or my mass? It's my weight. And technically speaking, scientifically, if you want to talk like the ladies on the video there, weight is measured in newtons. The other unit for weight is actually pounds. When we talk about kilograms here in Canada, that's actually a measure of your mass, right? So pounds and kilograms don't actually measure the same thing, although we, understand anything.
I would be able to explain that to Andy because he says that pounds isn't right when you talk about your weight.
Okay.
Because he measures himself in kilograms.
He measures himself in kilograms. Yeah, that's actually a mass unit. Okay. I'll try to do that for you, Dan. I'll show him a video.
What is the difference between mass and weight? I think it's something that a lot of people are confused about. They just think that anything that's big, like this car.
As always, you write down whatever you want to. If you want to sit back and enjoy and print it out later at home, you go right ahead. If you want to write every second letter, I don't care. I wouldn't suggest that. But. An object's weight is simply a measure of the force of gravity on that object at that particular instant. Since weight is a force and gravity is acceleration, we get Fw is equal to mg. I'll pause because I'm way ahead of you. We're trying to distinguish between weight and mass. So an object's weight is simply a measure of the force of gravity on the object at that particular instant. Weight is a force, gravity is acceleration, and we get Fw equals mg, and we've used that already, right? Where Fw is the weight. Weight force is what I call it. Some books will call it just big old W. Some books will call it Fg, force of gravity. I use Fw, the weight force. M, of course, stands for mass, and that is in kilograms. And G is the gravitational field strength, which on Earth is 9.8 newtons per kilogram. Every kilogram is 9.8 newtons. So my 850 newtons will tell you what my mass is in kilograms, right? Divide by 9.8. Of course, the greater the mass, the greater the weight. Right? If I lose a few kilograms, I will weigh less. Of course, G is constant, more or less. We assume G is constant throughout the world. We know it changes from place to place, but it's negligible. So now, how does, like I'm standing on a flat surface, not moving, how does me taking this on a moving elevator change things? Or does it change anything? Do I still weigh what I weigh? There are changes. Exactly. Okay? Again, you don't have to write it all. This is just sort of my note, my starter for the discussion. So for example, when you stand on a bathroom scale, and you need to draw the picture, so why write every word? The scale reads the amount of force that you're exerting on it due to gravity, and most scales will convert that to mass units, kilograms, or many of you in pounds, right? Technically a weight unit. If you are filling air in your tire, what's the units? Anyone know? PSI. Pounds per square inch, Dan. And pounds refers to force, not mass. per square inch, right? PSI, pounds per square inch. It is a weight. What's the other one? The other unit for air pressure, do you know? It's on some of the digital readouts have it. Some tires will have it on there as well. Most tires still say PSI. Anybody know? Kilopascals. Pascal is the unit of pressure. And after Blaise Pascal. Yeah, kilo, 1,000 pascals, like kilograms. Okay, so remember Newton's law says there's an equal and opposite reaction force. The scale exerts an upward force on me. So if I need to hold on a sec, stop. Listen. If gravity's pulling me down with 850 newtons, I'm pushing on the scale with 850 newtons. How much does the scale push up on me? 850 newtons. Excuse me. Equal and opposite. That's how the scale knows. This upward force is known as the normal force, and we've drawn diagrams about that. And it always opposes gravity. Okay, suppose we took the bathroom scale onto an accelerating elevator. Also suppose that I have hair and decide to wear suspenders. I'm not sure why. You write, don't write, just listen. Listen, don't write. I'll give you time. Trust me. You ride the elevator while standing on the scale. Since the elevator and thus the scale are accelerating you up in the air, right? Imagine me being accelerated in the air. Is there a force on me up? There is. Is there a net force on me? There is. Is it greater than 850? Yes. If it was only 850, I would just be either at rest or constant speed. But because I'm accelerating, there has to be greater than 850 newtons up, right? So we must have, since the elevator and thus the scale are accelerating you up in the air, it must be applying a greater normal force on you, which means in turn what? Because the scale is now applying more than 850, let's say 900. If I got 900 newtons on me, I say, well, I'm going to push back the same amount. 900 newtons down, I weigh more. I weigh 900 newtons because I'm accelerating up. Since you must react with an equal and opposite force to keep Newton happy, you appear to weigh more because the scale doesn't know the difference between riding in an elevator and simply a person with a greater gravitational pull. So because of that equal and opposite reaction force, you weigh more. I'll go through it again, right? Force is on more on me, 900 up. I decide equal and opposite, 900 down. I weigh more. And you feel it. You actually feel it when you're in an elevator, right? Okay, so does that make sense to you guys? Why you weigh more in an elevator accelerating up? Because I'm going to ask you on a test. How come you weigh more on an elevator accelerating up? That's why. Plus that couple times that I did the explanation. What would happen if you were to ride the elevator down? Okay, just listen. Don't write, just listen. Let's take my imaginary elevator to the top of the CN Tower. Okay. And as I fall away from the top, I am accelerating, right? How much force is required to hold me up? Very little. I'm accelerating down, right? I'm letting gravity do the work. So how much force do I push down on the scale with? A whole lot less. The scale doesn't need to push up to hold me up because it's letting me accelerate down. And in fact, I end up weighing less, right? So if you were to ride the elevator down, you'd be pushing less on the scale and thus way less. And I have a little sort of animation to show you as well. But before I do that, okay, so again, way more at the bottom, way less at the top. Okay, so can you see that? It's kind of small, eh? Let's see if I can zoom in here. Oh, that's good. Okay. 3 states of motion during a journey in an elevator. Pay attention to each state. We shall find out how the net force is related to acceleration. So, the guy's put on his jacket now, so he's no longer just standing there with suspenders, and he's lost some hair. The elevator is initially at rest, and then it begins to accelerate. The elevator is now accelerating, and the man feels heavier. Why does the man feel heavier during acceleration? How come? If we draw a free body diagram, the Earth's gravity pulls on the man, W equals mg. This is just the man's weight when he's at rest. The floor of the elevator exerts the force R on the man. How is R bigger than mg? It is. How come? Because he's got to be accelerated. There's a net force up. In this case, R is greater than mg, right? And R minus mg is equal to ma is greater than 0, i.e. the net force R minus mg accelerates the man upward. The acceleration is greater than 0. By Newton's third law, the man also exerts a force of magnitude R on the floor of the elevator. Now, this is important here, actually. This is the free body diagram on the guy, the man. Is he accelerating upward, Andrew? Are the forces balanced? They are not, which means there's a net force, which means there is a acceleration. The equal and opposite is not equal and opposite on the man. It's equal force on the man, and then opposite equal force on the elevator floor. So the R, because the elevator is pushing young up with R, we have an R down as well. And by Newton's third law, the man also exerts a force of magnitude R on the floor of the elevator. Since R is greater than mg, the man becomes heavier. Does he actually weigh more? Gravity is still the same force on him. Does his apparent weight change? Yes. His feeling of weight changes. The man gets heavier. After acceleration, the elevator begins to move at a constant velocity. You've all been on, well, maybe not all, many of you have been on elevators that are really tall. After you get going, you feel okay, right? Then when you get to the top, what happens? Yeah. Constant velocity. Man weighs as if he's at rest on the ground. Why does the man weigh as if he's at rest on the ground when the elevator is moving at a constant velocity? The answer is no net force. Man's weight, R, balanced, equal and opposite. R is the same. The man weighs as if he's at rest. Now the elevator begins to decelerate. He feels lighter. How come? Not as much force pushing up. We're slowing down. There's the man's weight. The R is less. How come? Doesn't have to push as much. He's got two eyes.
Two pupils.
Okay. So because the R is less, the R on the elevator is also less, he feels lighter. He pushes on the scales with a lighter amount. There we go. Okay, so I've explained it a couple different ways. I'll post that link as well so that you can read that. But what you're really interested in is how do we solve problems, Mr. Bennett? Because we know that you're going to throw problems at, right? You should have this already typed, right? You should have that sample question in that little package where it was sideways. We'll look for it. The sideways package. Okay. So, example number 5, a man standing in an elevator has a mass of 60 kilos. What is his weight if the elevator is stopped? If it's accelerating upward from the ground floor at 1.5 and so on and so on. And we're, of course, assuming down is negative. Now, I will have to warn you, the signs get really weird here. Okay? And there's going to be certain parts you're going to like, I don't quite get why the sign's like that. And I've always struggled with explaining this to kids. Suffice to say that when we're all done, I'll give you sort of a kind of a rule that will make sure that you get it right. Okay? Okay. The way I'm going to try doing it this show, you can see if this works any better. The weight force, mass times gravity. Right? 60 times minus 9.8 minus 588 newtons. That minus 588 newtons is how much is pulling down on me. 850 newtons, right? But it's not a measure of the normal force. The normal force is what direction? Up. Okay, so that 588 And again, here, this is where these signs get all weird, right? The normal force that's being measured. That's my weight. So I'm going to go with, therefore, normal force. Hang on, Alex. Don't let me lose my train of thought here. My normal force, my weight, is going to be 588 newtons. And newtons. Okay, Alora.
Archie says it seems that dad's a positive.
Yeah, I know. I'm trying it different this time. I'm hoping that I'm not going to confuse you. Because it really should, negative is down, right? I switched it to positive and it sort of got away from that whole sign thing, but then it still ended up causing me grief, so. But thank you. Okay, so 508 newtons. Now, that's if he stopped, right? At rest, sitting at the bottom of the CN tower. Now, if you accelerate upward from the ground floor at 1.5 meters per second, right away, after what I told you today, you should know that you weigh more, less, or the same. More. Right? I'm going to need a number that's bigger numerically than 588. Okay? So, and again, hang in here with me. I'm trying something new this year. I'm going to say that the apparent weight force, FWA, apparent weight force, it's kind of writing it backwards. Braden, you got to watch. Important. I don't want to have to explain it to you again later. Now I'm explaining to you. FWA is going to be equal to that weight force, let's do it like this, plus mass times acceleration. His apparent weight is that weight, 588, plus, what's his mass? What's his acceleration? 1.5, and that is upward. So it's whatever his weight was before, plus another 90 newtons. 678 newtons. He now weighs 678 newtons. He weighs more. How come? He's accelerating up. How much extra force is accelerating him? 90. Does he weigh more, Braden?
Yeah.
How much more? Come on. I'm helping you out. How much more? Did he?
Yeah.
Wouldn't want to waste time by saying 90 again. I'll just say I already said it. Okay, 678 newtons. Now, what if you're slowing down at 2 meters per second squared as it approaches the top floor? As you get to the top, you're going to weigh less. How am I going to write that out? Most people can sort of figure out the math, right? It's sort of how do you write it? How do you express it? That's the hard part. So I'm going to again say apparent weight force, FWA, is now the weight. Again, I'm going to say plus mass times acceleration, but this time the acceleration is actually negative, down. Oh, what's going on? 60 times minus 2. 508 minus 120. Or 468 newtons. Does he weigh less? 468 newtons. How much less? 120. Is it making sense? The next two, accelerating away from the top floor at minus 1.8 and slowing down. As you accelerate away from the top floor, do you weigh less or more? Less. As you slow down when you get to the bottom, do you weigh less or more? More. Why don't you try those two? I want to make sure I can do it, actually. Okay, apparent weight force is weight plus mass times acceleration. The guy has a weight of 588. This time we are accelerating away from the top floor at plus 1.8. Oh. What do you put in for A? Minus. It's down. I'm actually liking how I've set this up this year. So what'd you get? 480 newtons. How do you guys feel about the setup? The positive and negative signs. You okay with it? I actually like this. Yeah. I'm wishing I had figured this out years ago. And then the other one's going to be 588 plus mass. This time when you get to the bottom, the acceleration is up. You weigh more. How much is it? 1.5. It's the same thing over and over again, isn't it? Yeah, it's going to be this one, 678. That's it. Way more at the bottom, way less at the top. Okay? Now, you've got, and I know there's only 15 minutes left. I don't want it to be binders closed like in the next 30 seconds, okay? You've got a whole bunch of problems. There's some weight ones in there that you've avoided. I'm hoping up to now you can now do them. I've got one more pre-test quiz. Then I got to talk about friction. I don't see us getting to it for Friday test. Thinking we're looking more like, it is a long weekend, isn't it? Ooh. We will reevaluate. We'll reevaluate later in the week. If we need to have it Tuesday, and you guys really want it Wednesday, then I may reserve the right to say, well, I got to go on. Okay, so you got some time. Don't pack up. It's not over. I'm just giving you time to work.